We're going to delve into the world of thermodynamics. Touched a little bit on it last time. So a lot of thermodynamics deals with just energy. Basically, it's generally done in terms of energy. I have a system with some initial amount of energy. I can put energy in, I can take energy out, and it can do work, or I can do work on it. So we do work on it. So this energy that's automatically in the system, we basically have two kinds here, right? In a sense. We've got macro and micro. So the macro being the stuff that we can measure, it's got a speed, you got a certain, it's basically mechanical energy. The micro is what's happening at the atomic level, or the molecular level. And this macro stuff, that's basically what we've done already. This is where we're sort of going to concentrate. We're going to lump it into this thing called thermal energy, which in essence is kinetic energy. But at the micro level, it's very difficult to do measurements on an individual molecule. So there's a whole lot of thermodynamics that is statistics. We will not get into the heavy statistics, but if you pursue physics, thermodynamics, you will work heavily in statistics. So I have a certain amount of energy to start with, plus I put energy in, take energy out, plus work is being done, and I end up with some final amount of energy. It's not a huge concept here. There's energy in, energy out. We're talking about energy transfer because of temperature difference. This is what we're going to label as Q, otherwise known as heat. If I bring the original energy over here, I have EF minus EO. In other words, I have this change in energy. And we're talking about thermal. Is equal to Q plus W. There we go. First law of thermodynamics. It's just conservation of energy. Trouble is when you start doing thermodynamics, or one of the issues, is that when you're talking about work being done, is it work being done on the system or work being done by the system? Because that definitely changes the sign of W. The work done on the system, we're adding work into it. If it's work done by the system, we're taking work out of it. And there is not a standard. Basically, the textbook at some point will say, hey, we're looking at what's being done on the system, or another one would say we're looking at the stuff being done by the system. Your textbook does the work, looks at the work on the system. So that's why it's plus W here instead of minus W. All right, so we somehow have this energy put into a system. So as energy goes into the system, if I'm looking at a microscopic level, I can have a change in kinetic energy at a microscopic level, which translates into a change in temperature. Or if I'm looking at some change in potential energy, this we're talking about is a phase change. In other it's liquid, solid, gas, transferring from one to the other. And with the change in temperature, we also have potentially a change in length, area, or volume. So, let's just start out with temperature. What is temperature? Besides a measure of the average kinetic energy of the particles.
It's a measure of their microscopic vibration.
Yeah, I would buy that. What systems do we use to measure temperature? What units?
Kelvin?
Degrees Celsius.
Degrees Fahrenheit.
Rankine.
There we go. What is Rankine?
Is it degrees Rankine?
No, it's just Rankine. Have you heard otherwise?
I thought it, I don't know. I read it one time in a chemistry book in high school.
Yeah, I've also seen degrees Kelvin in a couple of places, but yeah, that was my reaction. All right, so there's obviously a translation between these two systems here of some sort. What's the difference between Kelvin and degrees Celsius?
273.15.
That's it? Yep. So if I have some degrees Celsius, I add 273.15 and I get my value in Kelvin. What about degrees Celsius to degrees Fahrenheit?
It's like 1.8 plus 32. I'm not sure which way it is, but 1.8 or 9/5 multiplied by one of them, or 5/9 depending on.
Depending on which way we're going?
Yeah, I forgot which way. Which one is for what?
I did degrees Fahrenheit versus degrees Celsius. Let's plot it out. 0 degrees Celsius is what in Fahrenheit?
32.
And so I got that point, and then 100 degrees Celsius is
212.
I have a line. Let's put it into slope-intercept form. Degrees Fahrenheit is equal to something degrees Celsius plus something. Y equals mx plus b. What's b?
32.
And what's m?
1.8.
Yeah. Rise over run. So I got 180 over 100, 1.8. And if I wanted to convert the other way, let's just zip that out real quick. How would we divide degrees Fahrenheit? How would I find degrees Celsius?
Minus 32 over 1.8.
All right, so minus 32 over 1.8. Okay. What is Kelvin? Besides this magical 273.15 off of degrees Celsius.
Measure of kinetic energy inclusive of absolute zero.
Good, say it again.
A measure of kinetic energy inclusive of absolute zero.
I missed a word in there. You said a measure of kinetic energy
Inclusive
inclusive of absolute zero?
as zero.
So, what is absolute zero?
Coldest anything can go.
Sure.
In a sense.
There's some really bizarre definitions of temperature where you can actually get negative Kelvin, but that, yeah. In those situations, I think they're just playing math games, but some physicists seem to get into it. So if it's a measure of kinetic energy, if everything stops moving, that's when you have, like, it sounded like that was the intent, I didn't quite hear it the way it came out
Somewhat,
there.
yeah, just,
So absolute zero would be, go in, everything stops moving. All right, so since we get this number here from Kelvin to degrees Celsius, what about from degrees Fahrenheit to Rankine?
I looked up Rankine, it says it's Fahrenheit minus 459.67.
Let's see if we can do it without looking it up. How would you figure it out?
Convert from Celsius and, well, do some sort of conversion
Okay,
between Celsius, Kelvin, and Fahrenheit.
all right, so absolute zero is how many Kelvin?
0.
All right, which would make it how many degrees Celsius?
73.15, or no, negative.
Yeah, there's a big difference there. All right, so I got negative, so I got at 0 Kelvin, I got negative 273.15 degrees Celsius. We can pop that maybe into there. And what is that in degrees Fahrenheit? I feel bad for Rankine. He gets a unit named after him, which is great, but who uses it?
People who really want to stay in the US customary system,
Who is that?
a lot of Americans.
Yeah, but they aren't dealing in Rankine.
Negative 459.67.
459?
Yes,
Point,
67.
I believe that's the number that Michael had read out earlier. All right, so we have, and I just wanted to mention Rankine and bring that in here just as a nod. Just, I feel like his family deserves it. So that'll probably be the last time we mention Rankine. All right, so we have this we have a change in temperature, and so did any of you do the small little experiment at some point in your life where you take a jar that's hard to open and then you run hot water over the top and it expands? So you did? Apparently your childhood was not as misspent as some of us.
We would just smack it if that was anything.
Yeah, well, there are other ways, yeah.
I'm sure I'm missing something here, but when we did that conversion, did we forget about the plus 32?
Did we?
I don't think so.
Well, no, because we got the right number, but I'm just not sure where I'm missing something.
You multiply this times 1.8, then add 32. I got a parenthesis in the wrong spot?
I already, I added 32 and forgot about it. I'm sorry for interrupting.
Okay. And what temperature is degrees Fahrenheit and degrees Celsius the same number? While you're figuring that out.
Negative 11-ish?
No.
No.
How'd you get that?
I just pretended Fahrenheit was Celsius and then, oh, never mind. Divided by 0.8, so negative 40?
Yeah, negative 40. I was watching local weather years ago, and the temperature was they were talking about some place where the temperature was negative 40 degrees Fahrenheit. And one of the news people said, negative 40, and that's degrees Fahrenheit. And I thought, and degrees Celsius too. All right, so as we put heat or energy into a system, the particles are going to start moving around a little bit more, and it's going to expand. So we'll have some change in length of most objects. And I say expand, that's not true for every object. The water is a classic example where it will shrink at some point. But I throw this next one out, assuming that you haven't really dealt with this much before. Have you dealt with the thermal expansion formulas? Okay, and I hope it's not on your screen because
Just notes.
all right. What would it depend on? And the reason I'm asking this is when I was in college, I was looking for a summer job and in engineering, and they asked me this question. And so I'm just curious about how well I should have thought through it. I blanked on one characteristic.
If we're talking about the lid, I would say like the radius of it and along with the thickness of the material.
Okay, so basically size of the material. If we're talking about change in length, a one-dimensional aspect here, L. L sub I or O or whatever you want to use for the initial. That was the thing I forgot. Got the other two though.
Would it be the specific characteristics of the material?
Alpha. And I probably should have written that closer. One more thing.
It's not temperature, is it?
You said the temperature? Close.
Connecticut.
Farther.
Change in temperature.
Change it. So this alpha here, the coefficient of linear expansion, thermal. Coefficient of linear thermal expansion. There we go. Some websites abbreviate it as CLTE. This is going to be somewhere around, it'd be like 2.1 times 10 to the negative 6th per Kelvin. No units on top, Kelvin on the bottom, or whatever temperature you're working in. 2.1, let's make sure I remember that one correctly. This actually should be 23 is what I was going for. That's the value for aluminum. So let's just do a quick plug and shot. I have a bar of aluminum. We'll say it's 5 meters long. The width or thickness is tiny. So the width, thickness, much less than 5 meters. So we can assume a one-dimensional. I take it from 40 degrees Celsius up to 60 degrees Celsius. How much will that bar expand?
I got 0.0023 meters.
When What'd you get?
0.0023 meters.
0.0023 meters. Alright. Benjamin, you get the same thing?
Yeah.
Alright, so a little more than 2 millimeters, which isn't a particularly significant amount unless, of course, this beam is holding up something incredibly important and you just have everything measured just precisely. Generally for buildings and things like that, yeah, that's not gonna make much of a difference. If you're designing fighter jets, yeah, you probably want to take that into account. Buildings are designed to withstand considerably more than what is usually put through. All right, so, but in reality, we know this thing is going to expand in 3 dimensions. So let's say I've got a block here of just length, width, and we'll make that height and make that width.
What does K represent here?
Kelvin.
Oh.
Yeah, run out of letters, it is Kelvin. Unfortunately, it's the same symbol we use for kinetic energy.
It would be nice if it was degrees, and then it at least would be the same, and you could tell it's a unit.
Yeah, they're just messing with your heads. That's pretty much it. All right. So as I heat this up, it's going to expand in all 3 directions. So I have my initial volume, which is just length, width, and height. As it expands, I'm going to have L sub naught plus delta L times so my final volume. If we assume that each of them will expand by this coefficient, then, which for the most part is true for most materials, then this becomes L sub naught plus